Good morning, everyone, and welcome to today's lecture. This is lecture number 7, and in the previous lecture, we were dealing with work energy theorem and potential energy. We had seen the potential energy, and we had dealt with the change in potential energy. We have seen the definition of change in potential energy. Sorry. Remember, the absolute potential energy is not defined. What is defined is always the change in potential energy, and it is defined as negative of the work done. Do we remember this, everyone? Yes or no? Remember this? What we had studied in the previous class? Okay. We had also seen in the previous class that for gravity, we can if we take the ground level as the level of zero potential energy, we can then define the potential energy of any point which is up and any point which is down below ground by plus mgh and minus mgh. Do we remember this? Yes or no? Do we remember this? Please let me know. I mean, if you don't answer my question, I get confused. Okay. We had also seen the potential energy in case of body, if it is a rod, where how do you find the potential energy of that rod, whether it is vertical, whether the rod is at an angle. We had seen the potential energy of any cylinder, sphere. I mean, how do you find out that energy? You find out the center. We had also seen one example where we had a chain which was kept on a semicircular track, cylindrical track, and we had located the center of that thing, and we had found out the energy. Everyone understands this, the concept of potential energy? Yes or no? Okay, then in today's class what we will do is we will start with the concept of the conservation laws. The first conservation law is known as law of conservation of energy. Law of conservation of energy. Can anyone tell me what is this law of conservation of energy? Law of conservation of energy. Can anyone tell me what is this law of conservation of energy? No one has heard about this term, law of conservation of energy?
Matter either be created nor be destroyed.
Energy cannot be created nor be destroyed. Then it is
Convert into one form to another form.
yes. Energy cannot be created nor it can be destroyed. It can only be converted from one form to another. This is known as law of conservation of energy. Energy can't be created or destroyed. Whatever energy was created at the beginning of the universe, the energy still remains same. It is only transformed from one form to other. Now this law of conservation of energy, it is always valid. No matter what type of process you do, no matter what is happening in this universe, anything, We are just converting energy from one form to other. Everyone knows this, and we will keep it that we are not going to put anything here, not saying anything, not adding anything. It just remains like this because this is a universal law. No one can change it. We have not seen a process where we have created energy, and we will not ever see a process in which we can destroy it as well. Now, what this has got to do with what we are discussing now? Actually, this has got nothing to do with what we have discussed now. I just wrote it because sometimes what we are going to read right now and this one becomes confusing. And that is why I written the original law of conservation of energy. What we are going to discuss in this chapter is this law of conservation of mechanical energy. That is what we are going to study. Law of conservation of mechanical energy. I call it LOCME in short. What is this law? Law of conservation of mechanical energy. This is what we are concerned with right now. Mechanical energy. We have already seen what is mechanical energy. Now, can anyone tell me, have you heard about this statement? Sorry. Have you heard about this conservation law? Law of conservation of mechanical energy. Yes. Anyone has heard about this one? What does this law of conservation of mechanical energy state? Anyone? No one?
The mechanical energy remains conserved if the forces acting on the system are conservative forces.
Oh, great. Good. I did not expect that you would be knowing this. Law of conservation of mechanical energy. Can you repeat what you say? What you said?
The mechanical energy remains conserved if the forces acting on the system are conservative forces.
First of all, we have to understand what do you mean by mechanical energy of a body. So what is the mechanical energy of a body? What do you understand by the term mechanical energy of the body? Yes. What do you understand by the term mechanical energy?
Potential energy and kinetic.
Yes. Mechanical energy of a body is the sum of its potential energy. Now, this potential energy can be in the form of gravitational potential energy. This potential energy can be in the form of spring potential energy. This potential energy can be in the form of electrostatic potential energy. Whatever potential energies are there for this body, this law of conservation of mechanical energy states that if only conservative forces are present, and this is a very important if only conservative forces are present, if only conservative forces are present, then the mechanical energy ME of the body or system, if it is not a body, it consists of more than one bodies, of the system remains constant. If only conservative forces are present, then the mechanical energy of the body remains constant. So, mechanical energy of the body is equal to constant. That means mechanical energy at any point A will be equal to mechanical energy at any point B. Or I can say kinetic energy at A plus potential energy at B. Why I'm writing B? Plus potential energy at A will be equal to kinetic energy at B plus potential energy at point B. But this is only valid, all these three conditions, or this is just one thing written in three different forms, are only valid if what? They're only valid if, it's only valid if conservative forces are present. This is only valid if only conservative forces are present and non-conservative forces are absent. Now, in some cases, you can also apply this law of conservation of mechanical energy if non-conservative forces are present, but work done by those non-conservative forces is zero. So there could be a case where conservative forces, apart from conservative forces, non-conservative forces are also there, but they do not do any work. Well, in that case, if non-conservative forces are present but they do not do any work, you can also then apply this theorem, which is the law of conservation of mechanical energy. Law of conservation of mechanical energy. Now, we have seen two laws in this chapter, or two theorems, or two laws in this chapter. Well, which was the first one that we saw in this chapter? Some law, some theorem. We just saw in this chapter yesterday or day before yesterday. What was that? What did we study yesterday or day before yesterday? We had studied some law or some theorem. What was that?
Work energy theorem.
Work energy theorem. We had seen work energy theorem. And now we are seeing law of conservation of mechanical energy. You have to understand one thing. Work energy theorem is always applicable. You can apply work theories, work energy theorem, whether there are conservative forces present or non-conservative forces present or both absent. You can always apply the work energy theorem. But this LOCME is only applicable where? It's only applicable if conservative forces are present. This law of conservation of mechanical energy, or LOCME, is only applicable if conservative forces are present, but work energy theorem is always applicable. Whether or not conservative forces are there, or whether or not non-conservative forces are there, you can always apply work energy theorem. But you can only apply this LOCME when you are sure that there are only conservative forces present and non-conservative forces are absent, or work done by them is zero. That means this LOCME is a subset of your main set. Your main set is work energy theorem. In that set, you have all forces. But in LOCME, you only take a subset of it. where only conservative forces come, or work done by non-conservative forces becomes zero. So instead of calling it set and subset, I call it by a different name. I call this as the mother theorem. Why it is the mother theorem? It is the mother theorem, I call it. This is the mother theorem, and whenever you have a problem, you always go to your mother, and she has all the solutions. A solution may not be viable, but she always has a solution. This is the mother theorem, always applicable. Anytime, any problem, go to the mother theorem. But sometimes the mother may not be required, and you can just apply the daughter theorem. And this daughter theorem is only applicable when the conservative forces are present. So sometimes you may not require to disturb the mother because she might be old, and you don't want her to get involved. Let her take rest and enjoy her life, and then you can ask the daughter to help you out, and she is good enough to help you out whenever non-conservative forces. She does not like non-conservative forces. So if non-conservative forces are not there, I mean, the daughter theorem can help you out in solving a problem. So if you ask a question, sir, where should I apply this and where should I apply that, you can always apply the mother theorem whenever you feel like the daughter is not good enough. Well, but in most cases, and in 95-96% of cases, this daughter theorem is good enough to help you out, because non-conservative forces are not going to be present, and you can do the entire question with the concept of LOCME, or law of conservation of mechanical energy. Do we understand this, or this has gone above our head saying bye bye? Huh? Bye bye? Or when I was in my college time, I mean, I was given. I mean, I understood a concept why God has given us 2 years. Well, God obviously is very intelligent, and He knows that human beings need 2 years. Why do they need 2 years? Because if they hear something which is stupid, one ear becomes the inlet, and the other ear becomes the outlet. In, out of the system. That no need. In, out. But then sometimes you might hear something which is fantastic, so you get it in, and it gets into your brain, and it gets into your system, and your outlet is blocked. It acts like a non-written wall. Nothing comes from the inside. But if you hear something stupid, in, out, it does not go anywhere. It is a simple connection. It's a straight line. It bypasses your system, and it goes out of your system. So does it go in, or does it go out straight away? Have you understood this? In, out, are you using both your ears, or you are using one ear that you get in, and the outlet is blocked, it gets inside your system? So that is how things work, and this is purely mechanics. Your body is a pure mechanical system. It also has electrical and neuro connections, but basically mechanical. Everything just moves. This was the law of conservation of mechanical energy. We come back to this problem. Now, we had done this problem. We've done this problem previously. We've done this problem many times, 1,000 times, I think. A body of mass m is at rest at a height h. And if I drop it, what happens? It comes down. With what velocity does it hit the ground? We had done the previous problem. We had done this problem in chapter 1. We again did it here. Before we did it by the mother theorem, work energy theorem, we had applied from A to B, and we solved this problem. Now the question is, can you do it differently? Not disturbing the mother and taking help from the daughter. She's also smart. She also knows physics. And she also knows that there is no non-conservative force present here. So she might be able to help you out. So the question is, solve the same question, but now not using law of conservation, but not using work energy theorem, but by using the law of conservation of mechanical energy. Your time starts now. Let me help you out with this. How would I have done this? So first of all, I will draw a line so that we understand that this is different and this is different. Then I will write from where to where I am going to apply this LOCME. I am going to apply this LOCME from point A to point B. And first I write the statement so that I remember the statement. Total mechanical energy at point A is equal to total mechanical energy at point B. Now, whenever I talk about mechanical energy, potential energy will come. So then I have to take a base or reference whose potential energy can be taken as 0. So I take the potential energy when it falls on ground, the lowest point, as 0. Now, I talk about the mechanical energy at point A, and we must understand that mechanical energy at point A consists of two things. Kinetic energy at point A plus potential energy at point A should be equal to kinetic energy at point B plus potential energy at point B. Now, I just put in the values. Kinetic energy at point A is 0 because the body is at rest, plus potential energy at point A. I have taken the ground core potential energy as 0. So what is the potential energy of this point? We have already discussed this point. It is equal to plus mgh. Plus is already there. That must be equal to what is the kinetic energy at point B. I have taken that the velocity is v. So kinetic energy is half mv square plus the potential energy at point B. I have taken it as ground. I have taken it as the lowest point, and I have taken the energy as 0. We solve this and we end up with the same result, that velocity at the lowest point will be equal to root over 2gh. So you do it by the mother theorem, you do it by the daughter theorem, you end up with the same result. And that is how it has to be done. Do we understand this? Yes or no? Now we have done this. So we just applied the concept of law of conservation of mechanical energy and we ended up with our result. Everyone understands this? Yes or no? Okay, that takes me to the next question, and let me present the next question to you. And the next question looks like this. A body of mass m is placed at the top of this extraordinary looking hill, and it is at a height h. Now, whatever we are trying to do, we are trying to do it by the concept of law of conservation of mechanical energy. So it is at this point, and obviously it is at rest. So I will just keep it at rest. Now, when I allow it to fall down, do not go on that drawing. Sir, how will it come down? Sir, it will get stuck somewhere. Nothing of that thing is going to happen. It is going to come here. When it reaches this point B, if this is point A, what is the velocity at point B when it touches the point B? With what velocity does it touch the point B? There is no friction anywhere. Don't worry about the friction part. It is not there. You have 2 minutes to give me the answer and stay happy. So how are we going to do this? Well, we have got two options. Either we can go to the mother theorem or we can go to the daughter theorem. I mean, we'll just do it by the daughter theorem. Now, what are the two forces acting here? What are the forces acting here on this body? Yes? No one knows this?
Gravitational force, normal reaction force.
There are two forces acting here, gravitational force and normal reaction force. Normal reaction force is of continuously changing its direction, also magnitude. It is definitely may not be conservative. But what is the work done by this normal reaction force? Huh? What is the work done by this normal reaction force? Zero. So if it does no work, I am sure that the only force then doing anything is our old gravity, our old friend gravity, and this old friend gravity and LOCME go hand in hand. So I am applying LOCME from point A to point B, as simple as that. Total mechanical energy at point A must be equal to total mechanical energy at point B. So I must choose a point whose energy is taken as 0. That point is my ground. Kinetic energy at point A plus potential energy at point A will be equal to kinetic energy at point B plus potential energy at point B. Old method, nothing new. Kinetic energy at point A is 0. Potential energy at point B, which is h height up, will be plus mgh plus I have already written is equal to kinetic energy at point B. Let me call the velocity at v plus the potential energy at point B is 0 because that is my ground, that is my energy, 0 energy level. I solve this and I end up with the result v is equal to root over 2gh. I get my answer and I stay happy. This is as simple as it gets. No more complications. It can simply be done by the use of this daughter theorem. Do you understand this? Yes or no? Okay. So now we take the next step in evolution. What is the next step in evolution? Till now we have only dealt with one type of conservative force, that is gravity. The second type of conservative force is your electrostatic force, but this is not going to come in this year at least. So we can chill. But the third type of conservative force, which is our new friend, spring force, or spring potential energy, the energy that will come. Now let us dedicate some time to this spring force and the spring energy or whatever it is. Spring, our old friend, spring. Everyone everyone has seen what is a spring. Yes or no? Huh? There was a point in time when I was of your age, maybe smaller than your age, and springs used to fascinate me a lot. And there was a time where all these ball pens that we used, they had small springs inside them, and they khatka like this, they switch like this, khatka, khatka, and everyone used to play with those switch. These days they don't have it. They have this round thing, and it comes out. I don't like it. This one is the one that I like it. It has a spring inside it. And springs and magnets are the two things that always fascinated me. How lovely. Spring. What has happened to this spring, my what the hell? Now it works. All these gadgets, they sometimes get stuck. Spring. You have a wall, you have a spring attached to the wall, and then you have a mass attached. This is the normal way that you start anything of spring. Now, the spring in its natural length, we call that natural length as L naught, which is the natural length of the spring. It is neither compressed nor extended. It is at its natural length, nothing happens, just the body stays like this. You must understand that every spring has something known as the spring constant, K. Every spring has something which is known as the spring constant. You can call it K. Now, what does a spring do? What does a spring do? What type of question is this? Now, if I extend this spring, by applying an external force, if I extend this spring, and I think I have extended it enough, I have applied an external force and I have extended it by a distance x, which is obviously I'm extending it from its natural length by x. Then what happens? The spring starts to pull this block back. So the external force that I'm applying is definitely in the pink direction, but the force that the spring is applied is definitely in the backward direction. Do we know this? Yes or no? Huh? Okay, we know this. What next? We are going to now compress the spring and then see. We now compress the spring by an external force. Ding, 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 ding. The force that I am applying, or the external force, is trying to push it, but then the spring tries to throw it out. If you call one side as plus x, the other side becomes minus x. Doesn't matter, plus or minus x. Spring exerts a force, and it has been found out that this force that the spring exerts, if I write it vectorly, is directly proportional to minus of the displacement. Why it is minus of the displacement? Because the direction of this force is opposite to the displacement, and displacement is always measured from the natural length of the spring. This natural length of the spring in this case is also known as the mean position. Mean position. Do you understand this, or this is going above our head saying bye bye sir? हो गया आज के लिए काफी. We understand this. So now vectorly, whether it is case number 1, this is case number 1, or this is case number 2. In case number 1, I am extending the spring. In case number 2, I am compressing the string. I can write in both of these cases that the force exerted by the spring F will be equal to vectorly minus kx. Do we understand this? Whether it is in this case or whether in this case, this k is the spring constant of the spring. And if the spring is light, the value is less. The spring of this ball pen is a very light one. You can compress it with your own hands. Don't even, you can compress it with your fingers. But you might have also seen a spring which is on your bikes, which you ride. It takes a lot of force to actually compress it. There are springs in the shock absorbers of your car, more heavier springs, more weight to compress them. Then you have springs on the bogies of your trains, heavier spring. You can see these big springs and heavier. You have springs everywhere. Depending on the value of this force constant K, we'll have to put a lot of force if the spring constant K is more to compress it. That is the spring constant K of the spring. Do we understand this? Yes or no? Vectorly, you can write it like this. If you don't want to write it vectorly, you understand if the spring is compressed, it will push you. If the spring is extended, it will pull you. So that is the difference between a spring and a string. Up till now, in Newton laws of motion, we did not deal with springs. We only dealt with strings. Strings can only pull. I have a string. This is attached to a string. It can only pull. The string can only pull. The string cannot push. I cannot push it. I mean, this is I can push because this is a very heavier one. But if it is a wire, you cannot push anything with a wire. Right? Go back. You cannot go back. Cannot be pushed. But string can push as well as pull. So string is different than your string. String can only pull. String can only pull. Spring can pull, which is in the case of extension, and it can push when it is compressed. So that is the difference between a spring and a string. Do we understand this? So it has gone above our saying bye bye. Now, as soon as you have this force, now you understand that this is a conservative force. So if you are extending the spring, you are doing some work. If you leave that spring will come back to its original position. So it will give you that work back. So your spring force is conservative in nature as well. Spring force is conservative in nature as well, and we will see the relation between conservative force and conservative potential energy. But right now, if I, since this is spring force is a conservative force, if I call the energy in the mean position, the x is 0 and the spring potential energy us is 0. Spring potential energy 0. Then when it is extended, the spring potential energy becomes plus half kx square. So remember the what the 0 point for spring potential energy is taken when the spring is in relaxed state. No extension, no compression, no nothing. That is where you always take the spring potential energy as 0. You cannot take spring potential energy as 0 at some other point. That is not how it works. We don't have that choice here. So spring potential energy is taken as 0 when the spring in its relaxed, chilling out state, which all of you do. Then when the spring is extended by an amount x, the spring potential energy becomes plus half kx square. What will be the value when the spring is compressed by x from the mean position, from the relaxed position? What will be the energy? Extended, it is plus half kx square. When it is compressed, then
minus 1 by 2 kx square.
Minus half kx square is absolutely wrong. It is still plus half kx square. So spring potential energy is never negative. It is always positive. Okay. It is never negative. It is always positive. Why it is never negative, always positive? Because spring, when it is extended, it is again pulling you. So the spring is also coming back and force is also in the same direction. When it is pushing, when the spring is pushing, the spring force is also in the positive direction and the displacement is also in the positive direction. So never it becomes ulta. Do you understand what I'm saying? Here, as you can see, the spring force is in the backward direction. And when you leave it, the spring will come back in the backward direction. So they are in the same direction. It is positive. Similarly, when the spring is pushing you, both are in the same direction. So spring potential energy is never negative, it's always positive. Do we understand this? Or this is going about what I'm saying bye-bye? Huh? We understand this? Gone. Bye-bye. Okay. No bye-bye. Good bye-bye. So this is about spring, and then comes a sweet little question. You have a body of mass m attached to a spring, and I leave it slowly. What happens? Will the spring remain in its natural length, or will it get compressed, or will it get extended? Huh? I take the spring from here, attach it to the ceiling, and then place a mass on the bottom part. What happens? Will the spring remain in its natural length, or will it change?
Will change, sir.
Will it extend, or will it compress?
Extend, sir.
Okay. It will extend, but the block will remain in equilibrium. Find, that is the first thing, find the extension in the spring in equilibrium condition. Find the extension in the spring in equilibrium condition. I hope you understand the meaning of equilibrium. Yes or no? And the energy stored in the spring. You have 2 minutes to show me your talents, else I will show mine. It's a simple question that should not require rocket science. You said minus mg by k. I don't understand the meaning of minus. So if I don't understand the meaning, then I will have to do my own thing. How I am supposed to do this? So I draw a different diagram because I have no space left to solve this question. So what will happen here is if I call the natural length of the spring as L naught, which is here, the spring will get extended by an amount x. The weight of the block is the force which is trying to extend the spring. But now the spring will apply a force and it will try to pull it back. The force in the spring is F. Now this block is in equilibrium. Here comes the old friend from Newton laws. This old friend is like a bad dream, is not leaving us. And that is physics, my dear friend. The old friend never leaves us. Whether he is a friend or an enemy, he will remain with us throughout our lives. That is physics. So old friend, Newton laws of motion, equilibrium, new friend, spring, but the concept remains same. It is in equilibrium, so it cannot go dhar 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 dhar. It cannot go dhar 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 dhar. Then these two things will be equal. So the blue equation F becomes equal to mg, and the spring force is the new friend that we have created, that we have made. So this new friend is k into x naught, or k into x is equal to mg. From here, I will get the value of x as mg by k, and I still don't understand how did I get negative here. How did you get negative? The negative only means that the direction of force is opposite to displacement. I have just taken the direction of opposite. If I take the direction up, and then still I can't call it as minus mgx, minus kx. So the spring has an extension of x is equal to mg by k. Do we understand this? It has gone above what it's saying bye bye, bye bye, bye bye, bye bye. Gone above our heads? Do we understand this? Yes or no? But the next part of the question still remains. What is the energy stored in the spring? What is the answer for this part? What is the energy stored in the spring? Sir, we don't know. We have come today. I am new in the town. I don't know. It's a famous joke. I would have told you that joke. Someone someone is moving in a town, Hyderabad. Let me say that I am there in Hyderabad. Someone asked me, sir, what is the time? I tell me, I don't know the time. I am new in the town. So whether you are new or old in the town, you must know what is the time. Similarly, whether you are new or old in the class, you must know what is the energy stored in the spring. What is the energy stored in the spring? What is the energy stored in the spring? No one knows it. Okay, so the energy stored in the spring is simply half kx squared. So that is equal to half into k into mg by k squared. So the answer is half m square g square by k. That is the energy stored in the spring, my dear friends. Do we understand this? What was so difficult in finding out this energy? Half kx square you had to put. You'd already calculated the value of x. Half kx square. That's it. That's an introduction to spring and spring potential energies. We will continue our quest in the next class. So in the next class, we will be dealing with more problems on spring. That is in store for the next class. Spring will be coming back with a spring in its steps and troubling us with some of the problems. In the next class, I'll see you. We'll continue on with discussion, law of conservation of mechanical energy, and that is the last everything that we have to understand in this chapter is going to get over very soon. So we'll meet in the next class. Take care. God bless all of you. Bye bye.
Thank you, sir.
Bye.